today we are going to learn about electronic configuration in Spdf notation and orbital diagram. What is electronic configuration? It shows how the electrons are distributed among the various atomic orbitals. So we use hydrogen atom as the example with one electron. Why? Because its proton number is equal to 1. As long as the element is at the atom state, means no charge, the number of proton is equal to the number of electron. So 1 electron we are writing as 1 S1. And 1 is n value, and then S is referred to the subshell, and then the 1 over here is referred to the number of electron in the orbital or subshell. So the first method we are using to represent electronic configuration is orbital diagram. So electron of oxygen atom is 8, so we assign 1s2 2 electron, 3s orbital 2 electron, and then 2p there are 6 electrons. We can represent in box, platform, or concentric circle, but I encourage every one of you use the platform. This is the easiest one. If we write in Spdf notation, we are writing as 1s2 2s2 2p4. The green color, the 1 2 2 actually is represent the n value principal quantum number, and then the blue color as sp actually is the L azimuthal quantum number, and the 2 2 4 in red color is the number of electron in the subshell. As we know, S orbital maximum 2 electron, P orbital maximum 6 electron, and then D orbital maximum 10, and F orbital maximum 14 electron. So while we assigning this electron, right, there are 3 rules we need to follow. The first one is Aufbau principle. How to define Aufbau principle? Electron fill in the lowest energy orbital first and others orbital in order of ascending energy. So we must apply this diagram. So 1s, 2s, 3s, 4s, 5s, 2p, 3p, 4p, 3d, 4d, 5d, 4f, 4f, 5f. Why there is no 1p? This one we discussed already during 2.2 about the NLMS rules. 1p is not allowed. Why? Because when n equal to 1, L equal to 0. So 0 only 1s is allowed. So 1p is not allowed. So we fill in according to this. We fill in 1s2, okay, like staircase, followed by 2s2, then 2p6, 3s2, 3p6, 4s1, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 4f14, and then 5d10. The second rule is Pauli exclusion principle. According to Pauli exclusion principle, no 2 electrons in the same atom have the same 4 quantum number, means the same set of NLMS, or in other words, each electron must have different set of quantum number. We look at the example for helium. There are 2 electrons, 1s2, so the n value is 1, then the L value is 0, so m value is equal to 0, and then the s value, for this case both are positive half, and then for this case both are negative half, so it's wrong way. Suppose one positive half, another one's negative half, so these are the correct set of quantum number. So even though they are at the same orbital, they are having different set of quantum number. Okay, third rule is about Hund's rule. Hund's rule stated when electrons are placed in a set of degenerate orbital. What means by degenerate orbital? A group of orbital of identical energy, for example 3p orbital and 5d orbital. So in this case, okay, there are 3 electrons for the 2p orbital upwards, another 3 electrons for the 2p orbital downwards. So each orbital is filled singly with the electron of parallel spin before the electron occupy the orbital in pairs. So for example, in this case, okay, carbon there are 6 electrons, so 1s2, so this one according to Pauli exclusion principle must have different spinner, and then 2s2, and then 2p2. So there are 2 electrons for the 2p orbital, so have to singly fill first with the parallel, with the same spin, means parallel spin. Okay, so Hans stated electron occupy separate orbital rather than pair. Example, so write the orbital diagram for beryllium, which has 4 electrons. So 1s2, 2s. 2. Suppose this electron have to fill in the 2s orbital first, not here. So according to alpha principle, electron have to fill the lowest energy orbital first and others orbital in order of ascending energy. So the 4th electron is filled in 2s orbital but not in 2p orbital. So the 2nd and the 4th electron have to fill with opposite spin. This one is according to Pauli exclusion principle. Each electron must have different set of quantum number. So while you explain, okay, while you write the orbital diagram, should be no problem for you all. If the question asks you to explain, you have to explain like this. So according to which rules, and then start saying what, and then apply to that question. So remember, so like example, so this one according to Pauli say what, and then what should you do for this situation for beryllium with 4 electrons. So next again, which of the following is the correct orbital diagram for the ground state electron configuration of nitrogen, which has 7 proton number, means 7 electron, and then explain. So I assign this one as A, this one is B, this one as C. First we check. The correct answer is C. And then why A and B is wrong? Check. So A does not obey Pauli exclusion principle. You check for this one. No 2 electrons in the same atom have the same 4 quantum number NLMS. So for the 2nd electron over the 2s orbital have to fill with opposite spin. Okay, how about B? Here does not obey Hans rule. So you define what is Hans rule and then say the 3rd electron over here, right? Okay, of the 2p orbital have to fill in over here at the 3rd column of the 2p orbital with parallel spin, not the 1st column of the 2p orbital with opposite spin. Okay, option C, yes, obey Pauli. Okay, opposite spin, and then obey Hans rule. Okay, singly fill at the degenerate orbital before pair up. So we always must keep in mind the maximum electron for S subshell is 2 and S2. For P subshell, 6 and P6. For D subshell, 10 and D10. And then for F subshell, 14 and F14. Each atomic orbital can only accommodate or place a maximum 2 electrons. So this is one orbital, so maximum 2 electrons, mass with opposite spin. So now check for next example. What are the possible quantum number for the last outermost electron in chlorine? So first of all, you must know what is the proton number of chlorine, 17, so which has 17 electrons. So you have to write down the electronic configuration, 1s2, 2s2, 2p6, 10, 3s2, 3p5, so 17. So the outermost means the 3p5. And then possible quantum number for 3p5. So we know that 3p, n equal to 3, okay, L equal to 1. So m equal to -1, 0 or positive half, and then s equal to positive half or negative half. Because the question just say what are the possible quantum numbers, so we can answer like this. The electron configuration of a neutral atom is 1s2, 2s2, 2p6, 3s2. So now the question asks, write a complete set of quantum number. For each of the electron, name the element. So based on here, right, the question one, set, and then each electron. So I have to write down the quantum number for 1s2, 2s2, 2p6, 3s2. I have to write down all. And then don't forget there is another question, name the element. So we check, total there are 12 electrons. 12 electron, this is neutral, means 12 proton number, so we can check for the least constant. Okay, so we know that the element with 12 proton number is magnesium. Okay, so let's continue, write a set of quantum number. So for 1s2, 100 positive half, 100 negative half. 2s2 is this 2, and then 2p6 there are 6 answers, 6 possibility, because the m value -1, 0, positive 1, And then the spin quantum number, there are 2 positive half and negative half. For the 3s2, again 300 positive half and 300 negative half. So these are the set of quantum number for each of the electron. Okay, next. 5. Okay, this one higher level. Okay, indicate the total number of p electron in nitrogen, s electron in silicon, 3d electron in sulfur. So the proton number is given. So the first thing we need to do is write down all the electronic configuration for each of the element and then identify the p, s, and then 3d electrons. In this case, nitrogen. So 1s2, 2s2, 2p3. This is the electronic configuration, and then the question asks about the 2p electrons. So total there are 3 electrons. So second one, okay, 14. So 2p6, 3s2, 3p2, and then the question asks about the s orbital. So total there are 6 electrons for s orbital. And then the third one, 16. So 3s2, 3p4, and then there are no d electrons. Okay, clear? So now, just now we learned how to write the electronic configuration for an atom. Now we proceed with ion. Always remember, we must write down the electronic configuration of the atom first, even though the question asks for the ion. So given the proton number 23, so we must write down the electronic configuration for vanadium atom, which has 23 electrons. So 10, 20, 23, so 3d5. Now you need to rearrange the electronic configuration according to n value. This one I keep on remind my student must follow the n value. It means 1s2, 2s2, 2p6. So this is n equal to 2, and then 3s2, 3p6, 3d3. This is n equal to 3, and then followed by n equal to 4 for s2. Why? Because when we want to proceed the electronic configuration for iron, 5 positive, we are going to remove the electron from the highest n value first. So meaning that in this case, we are going to remove 5 electrons from the 3d3 and 4s2. The first electron is removed over here, 4s2 followed by 4s1, 3d3, 3d2, 3d1. So and then we get the electronic configuration for vanadium 5 positive is this: 1s2, 2s2, 2p6, 3s2, 3p6. Always remember, when you write down the electronic configuration for iron, must start with atom first. So that's all for today. Don't forget to follow my IG at ChemiComSL. Subscribe, like and share my YouTube channel ChemiComSL, and follow my Facebook ChemiComShirley. Hope you all learned something. Thank you.